So Ashvaya is a second-year PhD student at New York University Center for Data Science, advised by Professor Yang Le and also Professor Qin Yung Chung, and has a master in computer science from University of Massachusetts. Yeah, working at the her research interests mainly lies in the intersection of natural language processing and also computer vision, and she's interested in using information from multiple sources such as text, image, video, and speech to improve the common sense reasoning capabilities of machine. She also completed a research internship at Facebook AI Research and now is doing an internship at Google. So her work has received a Best Paper Award at the Representation Learning for NLP workshop at ACL 2019. So I think many of us has already had one-on-one meeting with her today. And so I'm now giving the time to our speaker. Yeah, please go ahead.
Thank you for introducing me. Good afternoon, everyone. I'm Aishwarya. I won't introduce myself again. I'm very excited to be here, and I had a lot of really nice discussions with many of you today. And I hope to meet you in person at some point. For this talk, I'll be discussing multimodal machine learning, and in particular, our recent work on modulated detection. I'll start with why this area interests me. So when we reason about the things in our world, we take information from what we see, what we hear, what we read, and so on. And we use all of these inputs to make decisions to understand what's going on around us. If our goal is to build smart AI systems that can help humans do everyday tasks, which at least is my goal, and make our lives easier, we have to give these models the same ability to reason over all of these modalities. So this is the agenda. In order to really motivate our work, I'll provide a very quick overview of tasks and datasets, as well as some important previous work that led us to where we are now. A lot of this is probably redundant here at Microsoft, since a lot of the stuff which I'll be talking about was made here. But bear with me, and I'll try to be quick about it so we can get to the second half, which is MDETR. So let's start with some common tasks and datasets for vision and text understanding. The first is, I'm also covering these because they're the same ones. There's a good overlap between the ones I'm introducing now and the ones which we report on in our paper. So the first one is referring expression generation and comprehension. So the one on the left is, given the bounding box, you need to describe the text, describe the contents of the box. And on the right is referring expression comprehension, which is basically, given the text, you need to return a bounding box corresponding to the text. On the right, we see phrase cut, which is a referring expression segmentation dataset. The difference is there are many instances of the same class which should be returned in this dataset, in contrast to referring expressions where generally there's just one box. It also has a very long tail distribution of concepts, which makes it a pretty interesting dataset to see if your model can generalize to these. Everybody's probably heard of image captioning, so I won't spend too much time. I just put it for completeness. And then there's this localized narratives dataset, which is really interesting, and it's something that I want to look into in the future, where given the image, you also get the mouse trace of the person describing the image. So you get very dense alignment between parts of the text and parts of the image. More recently, there's been a retrieval dataset called crisscross captions, where not only do you have image text and text image retrieval, but there's also image and text scores, which gives you more information about how your model is doing. Finally, we have VQA. This is on CLEVR, which is a templated dataset. The image part is pretty straightforward, but often you require many hops of reasoning to understand the textual part and answer the question. The generic VQA dataset, which is open-ended questions. It's an interesting task, and a lot of us have tried working on it. And then there's GQA, which is much bigger than VQA, still templated text, so it's not human written, but it's it's a very large dataset, so there's a lot that you can learn from it. Cool. So let's go to some influential early approaches. The first one is Show, Attend, and Tell, which is one of the earliest papers for attention-based learning for multimodal work. So it's like you use an RNN with attention to the visual features to generate captions. So at a high level, this is what the architecture looks like. You have the input image, some CNN, which extracts some features, and then the RNN basically predicts each word by attending to the right part of the image. And this was like a pretty big step in this area because it was the first time you could get interpretable, interpretability from your model. So here you can see when you're talking about a little girl sitting on a bed, most of the attention is focused on the little girl. Then another paper, seminal paper, which is super important to this entire field, is this bottom-up and top-down attention for image captioning and visual question answering, which also won the VQA challenge that year. The main idea here is to like attend over objects instead of grid features. And I have this here mainly because it's still used till date in most image caption, image and text tasks as the main vision feature extractor. So it's a paradigm shift from attending to grid features over the whole image to first detecting the salient objects using faster RCNN and then attending to these objects. So this avoids the wasted computation of attending over like useless parts of the grid where you only attend to the salient objects. It was introduced for the task of image captioning and improved state-of-the-art by a large margin. An important point to note here, and also like which will come up later, is that such faster RCNN-based image feature extraction does not allow for fine-tuning of the features in an end-to-end manner because it has non-differentiable components like non-maximal suppression. So using these features for downstream applications means the detector needs to be able to extract all the concepts that could be required for downstream reasoning. For example, if the VQA question is, what color shoes is the person in yellow wearing? You need to extract the bounding box for the shoes. And for this, the detector should have already had shoes in its label set, or else it would not be able to do this for you. So to deal with this, to cover a larger vocabulary at that time, they trained on attributes, and they had a head which predicted the attributes, 400 filtered attributes, and they had like 1,600 classes. Moving on, another line of work was basically using models to predict the explicit program, which is used for reasoning over the image, and then using this explicit program to build your neural network that will be used for the visual feature reasoning. So feel free to stop me at any time, by the way, and I know I'm going a bit fast, but that's because I expect like this to be not that new to a lot of you, but if there's anything that's unclear, please feel free to stop me. So in this paper, basically they have a seek-to-seek model, which is used to generate the programs in prefix notation. And the program is used to predict the order of the modules, which are stacked on the fly, that is used for the visual reasoning. And it's trained in an end-to-end manner. But a drawback of this line of work is that they can't really generalize to free-form text, which is an important feature in our work, mainly because there's not always like a mapping from free-form questions into their predefined grammar, because they can only handle a fixed set of vocabulary of in their grammar, and it can lead to bad performance when you use that free-form text. It only works on CLEVR because it's templated and it's generated from a fixed set of like 10 templates, all the questions. But as soon as you switch to like free-form questions like in VQA, it wouldn't really work. The last idea in this early approaches section is this feature modulation idea, which we will use in MDETR. So Film was the first paper to introduce this idea, and the main idea is like you use features from the text to manipulate the visual stream using affine transformations. It's a very straightforward approach, and unlike the previous paper, they don't need any ground truth programs to train their model. Conditioning on the text is done here at the feature level and not just to like reorganize the submodules of the network. And the approach is basically you feed in the text to the recurrent network, which here is a GRU. You take the final hidden state, and then you predict a gain and bias, which you can see on the right, which gets multiplied and added at each of the residual blocks, which is shown in the middle here. And they show that they get really good results on CLEVR at that time without like being costly in terms of like spatial resolution. So you can have bigger images also if you can use it on that domain. Okay, so that was a quick overview of things that I thought would be useful for introducing MDETR. And now in this part, we're basically going to look at some of the recent, well, since 2019 papers in the area of transformers for vision and text understanding. So as I see it, there's two main types where you have two streams processing separately and then having some cross attention, or having like a cross encoder model which processes everything together. And the main, the push was towards pre-training on massive data sets. It worked in NLP, so everybody was like, why not do it in vision and language too? So the first kind of this is like the dual encoder plus cross attention, where you have separate vision and text encoder, and then you use some cross attention layers to like learn the alignment between the two. The first example is LexMert. I guess you might have heard of this one. Just putting this here for completeness. The pre-training tasks are the standard ones: feature regression, detector label classification, cross-modality matching, and just predicting the text based on the image. This is like mass cross-modality language modeling. On the other hand, we have this paper, which was also from Microsoft, and it was a very cool improvement over the dual stream because it was a simplified model and used a single cross encoder to encode text and vision, and also introduced this word region alignment objective, which improved performance. And then finally, we have Oscar, which used also a cross encoder and basically solved the problem for regions being ambiguous and noisy, and added these object tags as anchors so that you can not, so that you can train faster or like converge faster just because you have this stronger alignment between the two modalities. Okay, so the main point I'm trying to make make here is that all of these previous methods are basically bottlenecked by object detection, and it all depends on what objects you found a priori. So you cannot reason over concepts that you haven't detected, right? One very cool piece of work from earlier this year was Winwell, also from this group. It was solving this problem by, pre-training the detector on all available detection datasets. Definitely a way to solve this problem, and we were really excited to see this because it proved that there's headroom in the object detection front of things in the vision and language space, because everybody was just like slapping bigger transformers or changing things beyond the detection phase and not really paying much attention to this. And this proved to us that there's a lot of headroom that can be achieved just because you improve the detection part of it. And they had very impressive performance on all downstream tasks. It is still bounded by a fixed label set. So that's what we're trying to solve in our work. So
hey,
now I'll
ask you a question.
Yeah.
Could you explain a little bit more? What do you mean the bottleneck is the object detection?
So what I mean is, if you want to generalize to a new concept or novel combinations of concepts, that's not possible if you haven't seen that combination in your label set before, mainly because the detection is done as a first step, and then you have the pre-trained detector's output, which is then passed to the vision and language part, right? Like as sort of like a post hoc alignment by using your transformer to understand what's happening. Sorry, I'm trying to see the face. Yeah. So so mainly what we're trying to solve is like not having to be like bottleneck. Basically, what I'm trying to say is that you have like 1600 classes or like 1848 classes, and basically when you are trying to detect something or trying to do some reasoning task, suppose VQA, and suppose like this concept comes up which you haven't seen before, and even if it's very close to a concept you have seen in your label set for object detection, you still won't have like a box for it, just because it's not trained to like recognize these this new concept. Does that make sense?
I still don't get it, but let me rephrase my question a little bit.
Okay.
So basically, the language provide a smooth label for the vision.
Yes.
So before the vision is discrete of the like a 1,000 classes.
Okay, yeah. So in all of the approaches we've talked about till now, which is like Uniter, Oscar, Venville, all of these things, you still have like this object detection step, right? Like you're saying, okay, I'm going to train my object detector on all of these data sets, which have some finite number of labels that you know to detect using that detector, which is trained on this data set. And when you're trying to use it for the vision and language task, you're basically going to first extract boxes based on this detector, and then feed the boxes that you found to the rest of the transformer. And whatever reasoning you can do in the second half depends completely on if you have detected that object which might show up in your image. Does that make sense?
Impeng, I think you are muted. Impeng, you are muted.
Okay. So basically, thank you, Peng Chuan. So basically, the bottleneck you refer to the classification task within the object detection. That means you want to smooth the label for the classification task in the object detection, right?
Precisely. Yeah, that's precisely what we do in our work.
Cool. Thank you very much.
Sorry, I should phrase it like you did. I will say that next time somebody asks me. Thanks. Cool. So let's look at our recent work. It's called Modulated Detection for End-to-End Multimodal Understanding. So the main idea is you only detect objects that are relevant. So instead of your standard 36 regions that you find from your pre-trained object detector and then try to do your post hoc alignment, what we do is based on the fact that you want to find the alignment in the words in free-form text and the objects in the image directly. So we no longer have this first step of detecting things and then feeding it to our multimodal transformer, just because of the whole process is inherently a phrase grounding or phrase detection, which we call modulated detection framework. So that's why I say we're no longer bottlenecked. So let's see what this means. Okay, so what is modulated detection, right? So the way I would define it is it's free-form text condition detection. So like we just discussed right now, it's basically smoothing the label space so that you don't have this fixed set that you can find things from. You can find anything that you can describe in text, right? And also, in contrast with prior work, we don't detect or don't provide to the multimodal reasoning module anything that is not relevant to the text. So if it's not part of the question or part of the the phrase or the caption, it's not going to be a box, which is not good if you're only giving that part. So in Venville, Oscar, etc., you're obviously only giving the boxes. You're no longer giving access to the rest of the image, right? So we don't want that, because if you're only finding the subset of boxes which are mentioned in the text, we still want to keep access to the rest of the image, which is why we also make sure that you'll see in the architecture soon that we also cross-attend to the whole image to make sure we still can reason about the whole image as about the objects as a part of the whole image. And as a result of this way of doing modulated detection, we're basically able to leverage the compositionality of language to generalize to unseen combinations of object classes and attributes. So for example, in this image, we've seen the concepts of pink and elephant separately, but we've never seen them together. But our model is still able to put these together and predict the pink elephant precisely because of this reason. Sorry, one sec. Okay, so again, to just explain what the output of our model looks like, as opposed to the image they have in the paper in Venville. We have on the left the typical output from the detector in Venville. Due to the setup of most vision and language models, it requires the detector to predict any object class and attribute that could possibly be useful to downstream reasoning, because if you don't detect it, you're not going to be able to reason about it. And this makes total sense to do this and combine data sets. On the other hand, MDETR is kind of more efficient in the sense that it only detects the objects that are relevant to the query. But we still train our model end to end, making sure we still keep access to the whole image so the model can reason about the objects using the whole image. Okay. So this is the main idea, I think, which inspired the project, because we felt that all of the prior methods kind of thought of phrase grounding. Yes, does somebody have a question? No? Okay, I just hear some noise.
Hi, Israel. I have a question for this slide. Yes. So could you explain a little bit more why phrase grounding is central?
Okay, so as I see it, when you're trying to like solve a whatever NLI, predict entailment, or like trying to do visual question answering, or like describe the image, I might be wrong, but the way I see it, you shouldn't be able to do any of these tasks without being able to understand how to relate the text to the image. Of course, if you give all the objects and then give the text and hope that it learns it post hoc in like some sort of like self-supervised manner or like semi-supervised, like not strong supervision manner, it might still work. And we've seen that, it works decently in terms of like we have comparison to VisualBot and like, other vision and language tasks, which models which do that. But I feel that if you want to like truly solve any of these tasks, your model should know exactly which part of the text talks about which part of the image, so that it can like reason about it. I think this is quite like fundamental to our approach. So like, yeah, I don't know if maybe as I go along, you'll see from how we've structured the model why this makes sense, if you don't believe me right now.
So I'm questioning this is grounding in which level is the most critical for this VL task. So for example, the grounding could be on the object level. So like the person hold the surfing board, right? So you grounding the person and grounding the surfboard. But sometimes your grounding could be on, if one bounding box cover both the person and the surfboard and say, hey, this is one person and a surfboard within this, but I don't need to worry about where is the surfboard and where exactly the person. So if you relax the grounding to each object, you can still do a good reasoning. So that's why I'm asking. So this is phrase grounding in which level? Oh, this is a distribution in which level is more critical.
Yeah, I mean, I guess this is kind of like how people feel about this image text learning in general. Some people feel like just having a coarse attention over the image is enough and is like a form of phrase grounding, like you say, right? Like if you just know the general area of where the person and the surfboard is, it's enough. But I guess it's just like a way of designing the task. Like this is like object-based semantics. So sure, you can always have a different level of abstraction, but this is just one that we choose. So yeah, I agree that saying separate objects is like maybe, I don't know, maybe there's somebody will design another method where the level of abstraction is different, but this seems to work. So yeah, I think at some level you need to be able to like relate the image and the text, and doing it at the object level seems to be useful. That's all I can say.
Okay, cool. Thanks.
Yeah. Okay, so let's look at the architecture. I'll first go over the prerequisites, which is basically DETR, which is the detection transformer, and then I'll go over to MDETR. Okay, so the key idea is that it's a end-to-end detection pipeline. Does not have any non-differentiable components, no non-maximal suppression. It's single stage. There's no like region proposals and stuff. And the architecture is purely an encoder-decoder architecture. Yes, it takes and with like a CNN backbone, because now we have like full transformer. So I should mention that. Yeah, so the main idea, I guess, is that the predictions are made in parallel directly as a set. It's not, it's different from prior approaches, which use, first a region proposal and then non-maximal suppression. And here it directly provides the set of objects. Let's look at what happens to an image. So it goes through the CNN, you get some grid features. It's a set of image features. So to that, we add 2D positional embeddings, and then it goes through a transformer encoder-decoder. The output of this is a bunch of box predictions. There's no sense of ordering in them. The predictions are like, so you can see here that for each of the boxes or each of the hidden embeddings which are predicted, there is an MLP which will be used to predict either no object if it doesn't think it should correspond to any object, or if it corresponds to an object, it will predict the bounding box and the class. On the target side, you can see that there are two objects here, and there's always this placeholder no object class. There's a bipartite matching that is computed between the predictions and the target, which is a 1-to-1 mapping, and it's computed in terms of a cost which is composed of the bounding box as well as like the class that is predicted. So it's the same as how we actually supervise it once it's matched. But this matching step is basically just going to tell you which target predictions to supervise with which of the targets, and the ones which are not matched to anything will all go to no object. So the classification head here is supervised using a standard cross entropy, and the bounding box head is supervised using a combination of L1 loss and generalized IOU. So let's look at what's inside the transformer encoder decoder. The backbone, which is just the CNN, gets the set of image features. Like I said earlier, this 2D positional encoding ensures that it knows like which basically feature came from which part of the image. That's given to the transformer encoder, and that processes gets you a hidden state of this feature. And then on the decoder side, we have these object queries. I usually get a lot of questions about this, so if this is not clear, please let me know. These are just learned embeddings. They're initialized randomly and trained just like any other parameters in the model with SGD. This is used to provide an upper bound on the number of objects that can be detected as part of this framework. So like, depends on the data set. Suppose it's COCO, they use like around 100 object queries. So at the output of the transformer decoder, once it goes through this decoder and it cross-attends to the encoder, so it still has access to the whole image. It will have this FFN, which is shared between all of these predictions, which predicts a class as well as a bounding box. And as I had described on the previous slide, at this point, there will be the Hungarian matching step, which will tell you which target to supervise for which of the predictions, and the ones which are not matched to anything will get the no object. And here the red and the yellow, for example, have been matched to these two targets. So they will get like, this loss from this. And for inference, it just like directly predicts. So that's DETR. And this is like exactly the detection framework that gets plugged into our MDETR pipeline. Let's look at MDETR. Okay, so we have this picture of a cat jumping over a fence in front of a yellow tree. It goes through a CNN, you get image features. The text goes through a text encoder. We used Roberta, but you could possibly use anything. We just stuck to using Roberta because we didn't want to be too different from like prior work so that we're comparable. The image features are flattened, and you basically get a set of image features which get the 2D embeddings just like in DETR. The text already has positional embeddings from Roberta, so you just concat them on the sequence dimension. So you get a very long sequence, which goes through the transformer encoder decoder just as before. So the main difference here is that once you predict these box embeddings, basically, the MLP, which used to predict the class label and the bounding box, no longer predicts an explicit class label. It instead predicts a distribution over the words in the sentence. So this will become more clear when I show you the loss function. But what you need to understand is that now we no longer have like, this fixed label set from before where you can only find the objects that, you saw in the detection data set. You basically align, you train the model to align each box to a particular span in the text. And when we do inference, basically we predict a softmax over the text and then threshold it at some value so that you can get the span or the entity of interest. And whatever is not mapped to to boxes in the image using the Hungarian matching step is again mapped to no object. Any questions? Okay. I'll quickly mention here the architecture modification that we use for visual question answering in case anybody's interested in using this for that task. So here it's a CLEVR image and a CLEVR question. What is the color of the sphere behind the green cylinder? So this part should look pretty familiar by now. It's the same as before. The only difference is, in addition to these object queries which go into the decoder, we also have QA specific queries. It's just a name we give to like a few more learned embeddings that you pass into the decoder. They get transformed by the same decoder, and at the output, instead of using this FFN to predict the tokens in bbox, we basically have question type prediction, which predicts the, like in CLEVR, you have counting or like attribute prediction or whatever, like there's 4 or 5 types. These are the, this is what predicts that. And then for each of the types, for counting, for example, you'll have numbers. For attributes, you'll have the colors or the material. And this is how we do the question answering task. I have this quickly in the end as well for GQA, but if you have any questions, you can ask me if the queries are not clear or anything of that sort. But the idea is that because it can find boxes in the image that correspond to the question, it should be really straightforward for the decoder to be able to jointly reason over like, things that it has found, as well as the image to give you the answer. And it's also a way to like get interpretability, because like suppose for counting questions, you can really see if it predicted that many boxes and answers the same number of like how many spheres are in the picture. It should like tell you the right number if the number of boxes is the same. It's a really nice way for like sanity checks.
Ashwaya, can I ask, for the QA specific queries, is it also random initialized, just like object queries?
Yep, it's exactly the same as the object queries.
Okay, thanks.
Sure.
Hey, Aishwarya.
Hi.
So can you please go back to the previous slide?
Sure. This one?
So yeah. So on the right-hand side, is there a specific process that you follow to create ground truth mapping between the text spans and the objects?
Yeah, so the datasets that we use, I'll like discuss it in more detail when we come to the pre-training part of the, like in a few slides. But I can tell you right now that we use datasets such as Flickr 30K, VG, which has VG regions, and referring expressions dataset, where they already have the annotations between which part of the text correspond to a box. So the bounding box of the corresponding to the text. So we basically, in our data loader pipeline, we have the correspond like a given box, and we construct basically a vector of like 255 and give like positive or like put a 1 wherever there is a, or actually it's not 1, it's like the normalized by the length wherever that part of the text is. So like for cat, it would be like, 0.5 in the beginning, for example. If that makes sense. I'm just going to show that on the next slide actually for the loss. So maybe it'll be clearer then.
Okay,
Give me a sec.
Yep.
Yeah, so this is what I was talking about. So this is how we like supervise this. The cat, for example, over here is going to have this distribution. So the ground truth distribution that we compare our prediction to with a soft cross entropy loss is basically this. So it'll be like a uniform distribution over all parts of the text which correspond to this box. So it doesn't have to be contiguous. It doesn't have to be only one. So it's a many-to-many mapping, basically. So this box can be like a cat with white paws jump over a fence in front of a yellow tree. They can describe like, bring up the cat again at the end of the sentence or wherever. And it should be like a uniform distribution over all occurrences of that entity, basically. And you can see on the in reverse, basically the white paws, it's one text span, which refers to 4 boxes. So all of these boxes will have the same ground truth, as a thing that they need to map to. Does this make sense?
Yep, thank you.
Cool.
So, may I ask you a question related to this slides?
Mm-hmm.
So because where is the noun, can you do this like in the unsupervised way, like a clip, find the one-to-one mapping between the vision and text and such, and then you don't need to know, you don't need to know where the ground truth, which region and related to which text.
But like our entire method is based on having, you know, like an alignment between parts of the text, which are taking the place of labels for each object. So how would it work without that? I don't think I got that.
So so for example, like this, all of the, you only keep the noun and like the verb and other stuff, you just remove it and then do the Hungarian mapping. Make sure one box related to one component. So of course, you know, some Pons object will be considered as a background, but if you just force that constraint, just have a box, have all of the non-text, and do the one-to-one mapping by Hungarian. Is that works or it doesn't work?
I'm not sure I understand. So the Hungarian mapping between a box and a target is one-to-one, but between the text and the box can be many-to-many. So you can have the same, like different text, which different spans, which all map to the same box. For example, if you have the sentence like a couple is standing in front of a cake, the man does blah blah, and then the woman does blah blah. So like the box can be like, you know, couple is for both of them, but then the man is referred to again. So yeah, I'm not sure if you're saying that you want to remove the rest of the words and all of the nouns in the sentence map to the same text. If that is your ground truth and that's what you train your model to do, yes, it will do that. And like, sure, that can be an output too, but I don't see how that's useful because, you know, you want to learn a alignment between like things in the image and text so that you can like generalize to new concepts later. If they're all mapped to the same object, it's not very helpful, no?
So I understand. So basically, if your mapping have some noise and it doesn't matter, right? You can still learn something. So what you just mentioned that is just has some noise when you do the alignment.
Okay.
Oh.
So I think maybe what will clear this up is the fact that here there is no like inherent notion of like the semantics of the object and the text, right? You're just like predicting spans, but the other loss function that or like the other objective that we have actually tries to make the representation of the object itself close to the text representation. So then you wouldn't really want that for like random words in the sentence with the object, right? Like, I don't think that makes sense.
Okay, you can move forward. Okay.
Yeah.
Thanks.
Maybe I don't get what you're saying, and we should like sync after the talk so that I can understand.
Yeah, sure.
Okay. So yeah, so this loss function is basically learning the, you know, kind of positional information between the objects and the text, but it doesn't really align the representations. So the second one is what we call a contrastive alignment, which might be familiar since like it's very common now, like slip style objective between the image and the text and stuff like that. Here we align the embedding of the object after the decoder to the contextualized representation of the text after the cross encoder. So it's already like had some time to cross, like basically self-attend to like the visual features or something. So how this works is like this is how we construct the ground truth. So if you have, this is a simplified version, like this might be further tokenized down, but let's just assume these are 3 words which get tokenized to 3 tokens. And you have like 4 objects here. So you can see that the word ball is basically aligned to the 2 balls, which are the red object and the dark green one. Whereas if you have like this object, it's mapped to like the word ball and yellow, which is like all the, you know, it's a symmetric mapping between the text and the object. And we average the info NC loss contributed by both of these directions. So it's like the positives, which you want to bring closer together, divided by the positives plus negatives, which is like the normalizer. And yeah, so this is kind of the loss function, which enforces the alignment between the representations of like the object embeddings that you get at the output of the decoder and the text contextualized embeddings. So in terms of like ablations, we basically have this on CLEVR, the reported architectures with both of the loss functions, and this is what we get. It's a 99 average precision on the modulated detection task. And if you remove the contrastive loss, you basically get 83.2. If you remove the soft token prediction, you get 87.7. So yeah, you can see that they're both important, and yeah, it's useful to have them both. We don't have this ablation on the fully like large scale pre-trained model, but probably the same. Okay, so let's now look at some results on synthetic data. This is first on CLEVR, and then we will look at the natural images results on Flickr, Coco, and VG. So on CLEVR, it's important to be able to find objects which are referred to in the intermediate reasoning steps, because as I mentioned earlier, there's often many hops of reasoning that are required. So an example here is like any other things that are the same color as the partially visible things. You can see here that it finds the partially visible thing and is able to like mark it correctly. And using this, it can find the fact that the bigger any other things which are the same color as this object. In terms of numbers, we improve on like methods which don't use ground truth program annotations, which is like the actual program that is executed to get the result. The NSVQA takes that as input to the model, whereas we don't. So this is a pretty saturated benchmark, so it's not very interesting, but we just know that it does pretty well. CLEVR Humans is slightly more interesting because it's free-form questions. So if you remember the inferring paper from Justin Johnson and all, where they actually predicted the program using and had the neural module networks, it doesn't do so well. This is what I was talking about. Our methods are able to do better, and I think this is mostly because of the powerful text embeddings that we use. Cogent is a test for generalization, which we don't do so well on. I think we just learned a lot of spurious correlations between the shape and size. And then CLEVR Ref Plus is basically just solved. We got 100 on the subset, like the accuracy is reported on this task on the subset where the referred object is unique. And yeah, so this is like a referring expression for CLEVR dataset. A note about combining these two types of data, because I'm going to describe our pre-training on the next slide. I just want to mention that in referring expression, the entire text is mapped, like it describes one object, but they don't give you individual boxes for subparts of the sentence. Whereas in Flickr and like all the other data sets, like the VG regions, which constitutes most of our training data, they do have annotations for every noun phrase basically in the sentence. So one small boy is basically this one, climbing a pole with the help of another. It's marked all of these things. These are model predictions, but they're correct, so that's why I just picked this. The point is that they actually give annotations for all of these sub parts. So to deal with that, what we did is run like syntactic parser and basically just get the root of the sentence for referring expressions, and use that to as the thing that the whole box needs to align to, just so that we have some alignment between the two. Okay, so let's look at pre-training. We have images from Flickr, Coco, and Visual Genome, so that count sums up to around 200,000 images, which is much smaller than the other datasets that train on like conceptual captions and SPU captions and things like that. We combine training examples across different datasets for the same image. So what does this mean? Here, I'm just going to show you an example of 3 different examples from the referring expressions dataset, where the first one is the woman in the gray shirt with a watch on her wrist. You notice that it's just the root that is aligned to the box, just because we have this problem where in referring expressions, the whole sentence is aligned, like I said on the previous slide. And then, so in the referring expression dataset, these 3 sentences and these 3 boxes correspond to 3 different training examples. But what we do is like take a particular image and find all the annotations that we can find from like Flickr, Coco, not from Flickr, from Coco and Visual Genome, which are from the same image, and combine them. So why do we do this? It's not like, it's not just to like increase density of data, but also quite important for our training, because our soft token prediction basically tells you the span, right? So if the span was just the root always for these kind of sentences, it would be kind of trivial and you don't really learn much. Whereas on the other hand, when you have these like 3 or more sentences which are combined together up to a max length of like 255 characters, the model really has to learn to look at the rest of the sentence and like understand the difference between the 3 instances of the same class woman. So here it's like the woman in the gray shirt with the watch on her wrist. It really needs to like look at the rest of the information to be able to do this. So after this kind of pre-processing from these images, we get 1.3 million aligned image text pairs, and we train on for 40 epochs using this dataset. All of the data and like the pre-training code has been released. So if you're interested in taking a look, it's on GitHub. So some qualitative results. I've shown you the one on the left. There's one which says a man talking on his cell phone next to a jewelry store. You can see that it is able to find a jewelry store. Here it gives you the prediction for man and for cell phone. This one I like, is pretty interesting, mainly because this concept has never been seen in training, but it's been able to like figure out that using the text and the image, basically it's probably talking about this. For Flickr, how we do the prediction is we basically predict 100 bounding boxes and use the soft token prediction to rank the boxes according to the score given to the token positions that correspond to that phrase, like the max over it. And there's 2 lines of work which strangely don't cite each other, where they have 2 different ways to evaluate the model, where in any box, basically, if you predict many boxes, it's considered a positive, like a success, if any of the boxes that you predicted have more than IOU 0.5 with the ground truth box. Whereas in the merged box protocol, you merge all the boxes corresponding to a particular phrase, and then you have to have 0.5, more than 0.5 intersection over union with the ground truth. So we have pretty strong results on both of these types of approaches, with like more than a 10-point increase on both. For referring expressions, we have these 3 data sets where it does a pretty good job at being able to distinguish between different instances of the same class, which is what this data set is supposed to be examining. Here as well, RefCoco G is considered to be like the hardest benchmark out of these 3, because it has pretty long referring expressions, and we have like a 5-point gain, which is much more than a lot of the papers which came out very recently. So these are like NeurIPS 2020 and like after. So yeah, we were happy to have like a healthy gain over those. So referring expression segmentation is, I find this interesting that this major league logo is like not a very common concept, and this like street lamp, which is like kind of a weird shape. And it's like, yeah, it's nice that our model is able to find all of these things and do well on the spacecraft dataset, which was released by UMass a short while, like last year or something, and we have a pretty big gain over the baselines that they released. Okay, and now we can talk about GQA, which is something that a lot of people are interested in. If you remember the architecture which we use for CLEVR, it's exactly the same. So we do the same thing where we divide the questions into types, where they're like object, category, category and attribute and things like that. In the same way we predict this. During inference, basically we just first predict the question type and then choose the one of the heads which correspond to that question type. Here we're
question about previous slides. So in the pre-training, have you tried during the test remove the text features and only have the image features as the input? Is that you can still detect those boxes?
Well, so wait, how would it know which ones to find? Like, it's kind of like the prompt given to the image, given to the model to tell it what boxes to find, right? So if you don't give any text to it, how will it know which boxes to predict? Like, it's trained to predict only the boxes that are mentioned in text. I guess if you don't give anything, I don't know how it would do it. Like that's basically like yeah.
From the detection, so I'm looking at this from the pure detection point of view. So let's say given an image, and so in your encoder, basically you're trying to encode every tokens and the vision features and their text features together. So, and my question is, if this kind of the supervision can help you encode the features without the text. So if during the inference we remove the text, we look at the features and we know, oh, where is the sofa, where is the bed, even though we don't know the text. So but that's the
how would you query the model? How would you query the model for like sofa and like the point of the text during inference is basically just to ask the model if these things are in the image. So like if you don't give anything, it's not going to return any boxes, right? Because it's been trained to like detect boxes from the text.
Yeah, for the object detector, for the detector, you don't have the text feature. You have an image, and you can also output about a lot of the box and given the class label for each box. So
you're saying
just
pre-train
text input. So I mean, I'm not saying this is doable. I'm asking this. So
yeah, I don't think if you just remove it, it will still work and give you all boxes. It will give you probably 0 boxes because it's depending on like the text feature to tell it which part of the image to look at. So if you don't give anything, I don't know what it would do. Like it probably just not predict any boxes because like it's bad at negatives currently. So I'll get to that because for pure 0-shot detection using MDETR just as is, it's not going to work because we didn't train with any negative examples, right? So if you just like over here ask for like some random kite or I don't know, an elephant, it'll probably still try to find something, mainly because it's just never been trained with negative examples. So if you don't give any text, it's like probably like not going to find anything just because you're not asking it to find anything. I don't think it'll work out of the box. Maybe there's a way to make it work like with some more like fine tuning in some way. I don't know.
So let's consider a special case. So let's say if let's say the sofa over here or nightstand. Let's look at the nightstand because it's already in the text. So let's say So let's say if you learn the visual feature and nightstand text feature are exactly identical. So if you learn these two features not aligned but identical, in that sense, you don't need this nightstand in the text because the features are almost the same, right? So then, given the image, you will see the nightstand is already encoded within that image patch or image token.
I'm not sure because I feel like the cross encoder is going to have the sequence of the entire image in text, and probably when the decoder is trying to predict this, it knows to look in like the specific part of the cross and the hidden states of the cross encoder, which takes both to know what to detect. So if it's looking at the image features also, but I feel like even I don't think it's redundant to have it over there. For example, is what I'm saying. Like it probably has information that at this position, these are the text tokens and this is the stuff I'm supposed to look at to find things. So if you just drop it out, I'm not sure what it would do.
I know. So let's say if it doesn't work.
Yeah. So how about let's move forward due to the time limitation? Yeah. I think that's yeah.
Sorry, Pengtran. I think this question is very important to me. So
okay.
I'm asking this.
So yeah, actually, well, we put it this way. So say if we fit in a text like locate all objects, or maybe not for objects, but like a more like high level concept, like locate all the furnitures, all the fruits, so on. Do you think it would work?
That should work. That should work. Like if you say just furniture, mainly just because the text embeddings of furniture is probably close to like nightstand and bookcase and stuff. So I don't think this would have worked if we didn't have very strong text features going in. But because of like being able to understand that some concepts are close together, it should be able to understand that. Like we found, like when you query like random things, it does find things even if like the exact object was not there in training, for example.
Yeah, I was really impressed by the 0-shot detection capability you showed earlier. So the one on Yo-Yo. So I'm wondering, like, say we put in locate all objects. So probably for the
but it's not a prompt, right? You have to remember it's not a prompt. So it's not going to parse locate all objects. You probably just say object, but I don't know what it would do for that. Honestly,
yeah, it'll be interesting to see.
There's a collab which we've released, and it's really easy to play with. So you can like try it right now if you want to.
Yeah,
I
awesome.
should have like loaded it so that I can show it right now, but maybe at the end of the talk, if we have time, we can try it together.
But do you think there?
You what?
Impong, you are muted again.
So do you think there exists a condition? Once that condition is satisfied, you don't need the text as the input. So given an image, you can do the rest of the thing. And how to achieve that condition? So what's that condition? We don't know. And how to achieve that condition is another question. But I feel that's important because when we do the VQ, so why we need the text? For example, given this image, if we know everything, the question should not be together with the image as the input.
Why not?
Because you have QA specific queries. So in the decoder, you only add the queries to the decoder and you have the fully understanding of the image.
Yeah, but the question is what is saying which part of the image you need to look at, no? So if it's a visual question answering question, like how do you answer the question without knowing what the question is? Sure, the answer is in the image. That's the task, but like you need the question to know what to answer.
And that's true, but your question don't need to go through the encoder. Your question goes through the decoder is enough.
Possibly, like we tried briefly to like condition directly the QA specific queries, for example, on the text, and that didn't do as well as the architecture I'm showing right now. So we had some like ablations on different kinds of architectures on how to introduce the text and which part of the model to do it. And we even had a model with like two separate cross attentions to like two separate encoders, but it seems this is the one that we finally converged to. So it's possible that, in the space of architecture search, we didn't cover something which doesn't include adding the text as input to the cross encoder. That's completely possible, but in our space of like search, we found this to work best.
Okay, cool, thanks.
Sure. Okay, so as I was saying, here we managed to do better than VLT5 in like Oscar, but nowhere close to Winville, still a long way to go. I guess we still need to like scale up the amount of images and the amount of annotations we can use because we're still not reaching the levels of the other papers. Let's look at some qualitative stuff. So it's cool that we can get interpretable predictions by doing stuff like what is on the table. You can find the predicted answer as laptop, and it knows that what should be the object that it's supposed to find. So here you can see the table is, you have a box around the table and what. On the other hand, you have what color is the train. Here also it gives you a box around the relevant object. So we think this is pretty cool. It can like give you like easy way to inspect what your model is learning. Some additional examples. The one on the left says a green umbrella, pink striped umbrella, plain white umbrella. This is just stuff that we tried for fun. It's all in the collab. You can also go try it out. The link will be in on the slide in the end. Also like more kind of niche stuff like a flowery top, a blue dress, and orange shirt. And then finally on the third one shows you that it doesn't even have to only be like salient objects in the image. We can also find objects by just referring things in the background. So you can see an electricity box. This is quite like not a mainstream thing, I think, in detection. And then like the car is pretty straightforward, but it's pretty much in the background and not like something which is of main focus. So it's pretty cool that we can manage to still get it. The limits to like doing out of the box zero shot detection, I guess a lot of people here have felt this pain, is that if you try to directly use MDETR, you're going to have a problem, as you can see in this image, mainly just because we've never trained an image, text, and box where the text doesn't correspond to the box. It's just not something we've trained with. And I'm sure if you like train with negative examples, it will go away. We briefly tried detection on Elvis. We didn't spend a lot of time optimizing this, but what we noticed is that if you like give the name of the class as the text prompt and the image and all the instances of that class as the positive instances of the object. Basically, this is how we construct the dataset for 1%, 10%, and 100% tuning and train the model. Importantly, for the negative classes, because in Elvis, it also tells you which classes are present and which are not, because it's a federated dataset. For the negative classes, we give like the text prompt for the text version of the name and just like, no boxes. So it knows that in certain cases, when this text is not there, you should not be predicting it. And we see that like over DETR, we have like a pretty high improvement on the 1%, which is like 11.2 compared to 1.9. Still far away from like, state of the art on this. And this is like a heavily tuned mask our skin that we got from some folks at Facebook. But yeah, when you go to like 10 and 100%, we think that because of like the extreme imbalance, like at 1%, we're still choosing one instance of every class, and that's why it's 1%. So it's not really imbalanced. But when you go to 10 and 100%, Elvis is extremely imbalanced in terms of like rare classes. There's very few training instances, so that makes a huge difference, and it like makes our model suffer a lot. And we think that this can be improved by using strategies like repeat factor sampling and ways to like help with the class imbalance. That's it. So key takeaways are you remove the dependence from pre-trained object detectors by building a framework that is centered around detection, no longer restricted by the fixed vocabulary of objects. So like someone mentioned, it's the classification head in the detector, which we're trying to do away with. We can detect anything referred to in free-form text and lets us find novel combinations of categories and attributes and gives us interpretable predictions. Thank you.
Yeah, any more questions? In fact, I have a question. Can you go back to the kind of Elvis example?
Yeah, one sec.
So I'm thinking how you really, when you evaluate the performance of MDETR on this detection dataset, how do you really do the inference? So what's the query?
It's just the name of the class. I talked to my collaborators after our chat actually, and it was like in the initial versions I tried using this is the class name, like this is car, this is a blah. Okay. But in the end, we just started using just the class name. So it's basically just a label.
But you concatenate all the class names together as a single query, or in fact, you do multiple query and
we
then
do multiple
the boxes.
Yeah, the second.
But then the inference speed
very expensive.
Okay, yeah. Got it.
Yeah, this is definitely not like a thing we would propose to anyone to do. It was just something like to test how the model does in this case. But yeah, definitely if this is the main goal of the project, the way we did it is not the way to go.
So a follow-up question is that, for example, maybe the Elvis have a lot of different object category, but what if you apply this model on Coco, and then you can connect all of their object category, for example, the age object category, into a single sentence as a query? So do you think this is doable or not?
You can try with our train model on, the non-negative sample train, but like the one, if it's classes which our model is seen, it'll like find you probably. I would try in the collab. Like I haven't tried this. It's an interesting question, but it's I promise the collab is very easy to use. It's like already set up with some images, and you can just switch it out and put whatever you want and test it.
Yeah, sure. Yeah. So thank you for the lovely presentation. I have just a quick question. You mentioned that you use the root of the sentence to create a pseudo mapping, right? So can you be more specific? Did you use a constancy parser or the dependency parser to extract
dependency parser? We use from Spacey, basically.
So usually in the dependency parsers, you have the root as a verb of that sentence, right?
Yeah, there was a bit of hacking involved.
Okay, then it makes sense.
Yeah. It was quite painful, but yeah, we had lots of if blah. But yeah, we released the data set, so at least that's useful to other people.
Cool. Thank you so much.
All right.
Hi, Ashwaya. I have another question, and related to your decoder. So basically, the decoder in the DETR original DETR paper, they trying to learn the relationship between the proposals and such that they can remove the duplicate. And so then now you add the QA specific queries, and those queries have some relationship to the final object and also have some relationship to the proposals, but finally consider as the background. So have you noticed any difference?
So I will stop you there. Sorry to interrupt, but the object queries don't take part in matching. So there's no like, it's not considered at all in the matching step. Only the first n object queries are considered for like the object detection part of it. I agree that the transformer decoder, in the decoder, it can like, self-attend to any part of it, and it probably like of course does, but it doesn't take part in matching. So there's no like idea of like the object queries, sorry, this QA specific queries being mapped to background or being mapped to no object.
But in your self-attention, when you do the inference, when you do the attention at the first iterations, do you know which one is the object, which one is the proposal? You don't know, right?
In DETR as well as in MDETR, the losses and the predictions are computed at every layer. So it's, if you look at the code, there's this --aux loss, which auxiliary loss, which is by default on, and which means we're going to be taking like the predictions at every layer, and they're all taken together in the loss.
Well, I understand that, but you cannot distinguish the and the proposals, right? So until you go to the final one and look at this, until you look at the scores.
I mean, they will change. Like each of the predictions from each of the layers, the matching is computed for each one of them, and the prediction is made from each one of them. So I'm saying the entire pipeline for like matching FFN and then the loss computation is computed at every layer.
But
so
that's for training.
You can check. You can, yeah, for training. What do you mean for inference?
The inference.
Yeah.
In the inference, you don't know, right?
Yeah.
So in the inference, your queries will attend to the object, will also attend to proposals.
Mm-hmm.
You cannot distinguish them,
I guess.
So in that sense, so what's the proposals? What's the role of the proposals?
By proposals, you mean like no object tokens? I'm not sure what you mean by proposals.
Proposals, for example, in one object may have several proposals on it.
Well, not really, because in DETR and MDETR, you're doing a set prediction of the exact number of objects. It's not that at some point it like reduces, right? Sure, like internally to the decoder, maybe like the matching at different layers changes because it understands that two of the things correspond to the same one. But at the final layer, you don't have like proposals and then NMS. The thing that it predicts is either a box or not a box. That's it.
That's true. That's for the training. But in the inference, let's say at the beginning you have 100 queries. That's 10 of them will be the object, and the other 90 will be proposal. And at the first layer, there is an overlap between the proposal and the object.
Okay.
Right?
Sure.
So in that sense, the proposal, even though finally output you have object, but proposals will cover the object. And at the end, it will be considered as the background, right?
Okay, yeah.
Then, but those proposals, your QA attend to those proposals and aggregate the information from those proposals. So how?
Yeah,
Right?
I mean, I don't think it's much of a problem because, yeah, I mean, yes, I agree. Like at different layers, there's going to be like some parts which are like going to be no object finally, and the QA specific queries are attending to it. But I think it can learn, like during training, it's learned to like attend to things which are useful to it. I don't know. I'm not sure like what happens to that level inside the decoder. I guess it would be interesting to see or like check that somehow, but yeah, I'm not sure.
Okay. Okay, thanks.
Nice.
Yeah, Ashwa, I have a maybe a hell of a question. So you mentioned that in your model, so it can simultaneously predict the bound box and also, for example, the answer to this question. So and you think this kind of determine so by determining whether this bound box match to the answer will help us to interpret whether the model actually is grounding on top of the question or somehow like that. So, but to me, because this, do you think this kind of correspondence between the box prediction and the answer prediction will exactly tell us your model are grounding on top of the visual input, because both of them are just learning from the data, and you just look at the output prediction of this model. So do you think this still actually is somehow learning some kind of superior correlation, or indeed the model can grounding the answer on top of this bound box, which was predicted by the model?
Yeah, I mean, there's always a problem in machine learning with the spurious correlations. And I would say like a way to make sure it uses it is to have like another module maybe which checks for consistency between what it's predicting as boxes and what it's predicting as answers. And maybe like, you know, again, make a loop around the model. But yeah, we're like exploring ways to make sure that the model actually uses the object queries to make the prediction and like try to improve on this. But for now, yeah, it's totally possible. It's still like learning some spurious correlation, I guess. But like as far as we can see, like most of the cases, it like does a reasonable job at giving you what the model sees and like gives us the answer. There are definitely some cases where we've seen that to fail, and you know that is concerning, and we're going to try and fix it.
Yeah, do continuously, for example, measure. Okay, so given the question, if your model predicted the correct answer, but the grounding is not good, I mean, the bound box prediction is incorrect, or the vice versa. Did you maybe observe this, or even quantitatively measure this kind of
We didn't compute this number, but yeah, it definitely happens. Like I've seen it. Like, is there a blah in the image, and like sometimes when it's getting the answer yes, I think the answer is just a function of the fact that it's a common answer, you know, like the normal problem in PQA where you can't always know if it's actually looking at the image or it's not. And when it like doesn't predict the right box, or that thing is existing and it finds the box and it's saying no, it's probably because that sentence has a high chance of being a no question, which is very common in like EQA, GQA, etc. So yeah, these spurious correlations that it learns is definitely a problem, and like we need to like make sure that the model is consistent with itself, and that's something that we're looking into now.
Okay, I see. Okay, great. Yeah, thank you.
All right. Anyone else?
So any other questions? Let's see. So if there's no more questions, let's thank the speaker again. Thanks Ashwaya for virtually visiting us, and looking forward to your kind of physical visiting after the COVID.
Yes, hopefully soon.
Yeah. Okay. Thank you.
Okay. Thank you for inviting me. I had a great time.
Thank you for the great talk.
Thank you.
Thank you.
Okay, let's end the talk today. Thanks.